Hello, I'm Dr. Matt Helmers with Iowa State University and the director of the Iowa Nutrient Research Center. We're fortunate to be out at one of the Iowa Conservation Reserve Enhancement Program wetlands today with Dr. Bill Crumpton that's been working on this technology for a number of years. And these practices are being put in place to help us reduce downstream nitrate delivery, intercepting that tile drainage and water and reducing nitrate delivery. Thanks for joining us today, Bill.
Glad to be here.
So one of the questions I would have is, these are being put in to help us reduce downstream nitrate delivery. How do they go about removing nitrate?
So the primary process involved in nitrate reduction in these types of wetlands, ones with really heavy non-point source loads, is denitrification. So denitrification is carried out by anaerobic bacteria. The heterotrophic bacteria, they use organic carbon as an energy source. They use nitrate as an electron acceptor rather than oxygen. And they denitrify nitrate to dinitrogen gas, N2 gas. That's 80% of the atmosphere.
So what impacts their overall nitrate removal or the performance of the wetlands? What are some of the factors that influence their performance?
Okay, so the primary factors that affect their average long-term performance is the amount of water that goes into them, so the hydraulic loading rate. That's the volume of water divided by the pool area. The temperature affects their performance. Nitrate concentrations, the higher the concentration, the more mass they remove. Those are the primary factors that we have some control over: hydraulic loading rate, concentration, and temperature. We don't have a lot of control over concentration or temperature, but we do have control over hydraulic loading rate. If we make the wetland larger, hydraulic loading rate will be lower. The wetland will remove a larger percentage of the nitrate that it sees.
So what might we expect as we think about different hydraulic loading rates and the size of the wetland in relation to the watershed? What might we expect for nitrate removal?
So hydraulic loading rate will be related to the pool area and the contributing area to that wetland. And people can relate to that a little better than just hydraulic loading rates, right? So a wetland that was 1% of its contributing area, right? So a catchment was 500 acres, a 5-acre wetland sitting at the bottom of it. That wetland would remove close to 50% on average of the nitrate that it sees.
So these wetlands, at times we'll see some of these wetlands with a lot of emergent or submergent vegetation. Does that vegetation matter as we think about the performance from a nitrate removal standpoint?
For habitat it matters a lot, but for nitrate removal, the wetlands will function with or without extensive emergent vegetation or submergent vegetation. The vegetation, especially emergent vegetation, greatest influence is it can affect the way water moves through the wetland, right? So if you had really dense stands of emergent vegetation and a channel down the middle that was open, then you'd get a lot of short-circuiting of flows. The vegetation would resist flow. The flow would tend to short-circuit down the middle of the wetland, down the channel. That would reduce performance. On the other hand, if you had uniform emergent vegetation across the wetland and the water was forced to move through it, you could improve performance because bacteria associated with the submerged portions of that vegetation, especially standing dead vegetation, could support denitrification, right?
So does it matter how deep these wetland areas are for nitrate removal?
It matters how deep, but they're designed within a fairly narrow bound, right? So the wetlands have to have at least 75% of the total pool area has to be shallower than 3 feet. You can have deep areas, but they can be no more than 25% of the total pool area, right? So the wetlands are, on average, very shallow. On average, they're about 2 foot deep. The average depth for CREP wetlands is about 2 feet. They may have areas that are 8 feet deep, but their average depth is 2 feet. So they're predominantly shallow margins with a little bit of deep water toward the middle, right? So there's not a lot of difference in the average depth among the CREP wetlands because of those constraints, right?
So you've been working on the design, monitoring of these types of wetlands for the better part of a couple decades. During that time, has the design of them changed to try to improve their performance from a nitrate reduction standpoint?
Yes, it has. Right. So the primary changes have been the use of submerged berms to make sure water didn't short circuit through the wetland. So we make sure all the prior channels in the wetland, those are plugged at intervals, and we have shallow submerged berms to make sure water moves in a fairly efficient manner and it makes good contact with most of the wetland pool. The other change that we've made is in areas where there are more erosive environments, higher energy landscapes, they'll build sediment detention basins upstream of the pool, sort of a forebay. So water flows in, hits a forebay detention pool that might be 10 feet deep, slows down sediment deposits there in that detention basin. It reduces the sediment load to the wetland, which extends the service life. But these wetlands have a really long design life as it is, but that improves it by reducing it further. And then that detention basin can be serviced every 10 or 20 years as needed. It could be dredged out again.
So we talk about nitrate removal. One of the things that I think is very unique about the Iowa CREP program is from the start, there's been a monitoring component associated with this. Right. So can you describe kind of how many of these wetlands you might monitor in a year and what you do to quantify their performance from a nitrate perspective?
So we monitor, have monitored over the past decade or more, 10 to 15 wetlands a year. We're shooting for 20 wetlands a year now. And the monitoring is at the inflow. We have automated samplers that collect a sample every 6 hours. Those are composited into a single daily sample. Same thing at the outflow. So close interval monitoring of the inflows and the outflows, plus grab samples every week to supplement that. And then we have flow measurements, continuous flow measurements, either at the outflow structure or in the channel, right? So close interval data on flow, temperature, and close interval samples. From the automated samplers operate from as soon as we're able to get them deployed in the spring after the snow melt is gone, and we operate them until they begin to freeze up. Typically now late November, early December.
So you mentioned when the auto samplers are out there, but if I understand correctly, your crew is out there even during those off months in collecting grab samples. And then what are all those samples analyzed for?
Yeah, so the samples are collected year round. The auto samplers only operate when the weather allows from the spring through late fall. But we collect weekly grab samples at inflows and outflows year round. The samples are returned to the lab. They're pre-preserved in the field as they're collected. They're returned to the lab. We do a full suite on nitrate and what amounts to total Kaldol nitrogen. So we do total nitrogen and nitrate, from which we can calculate the total reduced nitrogen or Kaldol nitrogen. And on phosphorus, we analyze total phosphorus and total reactive phosphorus. And we've done that on all sites for the past, more than the past decade.
So we've talked a lot about nitrate reduction in these wetlands, but you mentioned that in the monitoring, you're also analyzing for phosphorus. Do these systems remove phosphorus, and if so, how effective might they be?
So, yeah, the wetlands do reduce phosphorus, but nowhere near the efficiency with which they remove nitrate. Really relates to what the phosphorus concentrations are entering the wetland. If the phosphorus concentrations entering the wetlands are high enough, the wetlands reduce the phosphorus concentrations. If the phosphorus concentrations entering the wetlands were really low, which is unusual, but if they were really low, the the wetland can actually serve as a source for phosphorus, at least for a few years, right? Because these were former agricultural lands that were converted to wetland, right? So yes, they do reduce phosphorus, but we can't come close to meeting the nutrient reduction strategy goals for phosphorus using wetlands. I would suggest the same thing is true for every one of the edge of field denitrifying processes, saturated buffers, bioreactors, wetlands. None of those systems reduce phosphorus to any substantial amount.
You talked a little about the water quality aspect of these. Sometimes we get questions, what about, we're removing nitrate, we're converting that nitrate to nitrogen gas. What about greenhouse gas emissions from these types of systems?
Yeah, so I've had a couple of students that have, whose thesis research is focused on greenhouse gases, primarily nitrous oxide and methane. Nitrous oxide is a really big concern. So these wetlands, because they're continuously flooded, continuously anaerobic at the sediment, turns out that they're extremely efficient at reducing nitrate all the way to N2. So you can think of the fractional yield of nitrous oxide for every mole of nitrate removed, how much nitrous oxide is produced, and for these wetlands it's less than 0.5%. That's about the lowest of any of the denitrifying practices that we're examining. Typically the fractional conversion would be a few percent higher. So the emission rates from these wetlands average about what you get from a cornfield. Right? So if you had a cornfield and you convert it to the wetland, the emission rates are no different. The nitrate that you remove in the wetland, though, doesn't get denitrified further downstream in systems with higher nitrous oxide emission rates. Right? So you in effect are reducing nitrous oxide emissions overall, because this is a more efficient system to denitrify nitrate to N2 than, say, stream bed or stream riparian zone.
So we see kind of this ponded area behind us, a pool here. You know, one of the questions we might get, do these types of wetlands help in flood reduction?
It's important that people understand when we say flood reduction, we just don't mean every minor little increase in flow, right? So a flood reduction, you know, a large flow, these wetlands have no measurable effect on peak floods. They're designed to operate at full pool. They have little storage capacity because of that. And even if they were drained when a flow came, which you really can't do, there's not much storage capacity. So if you think about a 4-inch runoff event, right? That would put 400 inches of water on a wetland that was 1% of its catchment area, right? So a stack of water, what is that? 400 inches, you know, tens of feet high, right? So no, these are not going to reduce flooding, right? It's proposed a lot. And the proposals seem to assume that you've got a dry basin with some storage, and then you get a runoff event and you fill it. That's not the way these work, and even if they operated that way, there's not enough storage capacity to have a lot of effect.
So these types of wetlands, would they also provide some habitat benefit, and how might they be designed, or the buffer area around them, how might that be designed and maintained to enhance maybe some of those habitat benefits if they are there?
So they they provide substantial habitat. The buffers, so the average CREP wetland has a buffer that's over 3 times the pool area. So if you had a 10-acre CREP wetland, you might have 30 to 40 acres of buffer around it. And those buffers are planted with a native mix of grasses, prairie mix of grasses and forbs. So the same sort of mix you would use in prairie restoration, right? So a lot of buffer habitat. the pools provide, but between the emergent, submergent vegetation and the pool, they provide a tremendous amount of habitat. They're designed to be wet, right? So an interesting thing is that even during the most severe drought we've had in the past 15 years, these systems have not gone dry. Water levels have dropped, as much as a foot in some cases. But if you think about, they're receiving all of that subsurface flow from a really large catchment area up above. So they have a lot of water supply. Right? So they tend to be the last places in the landscape that do go dry. During drought years, that can really be pretty critical habitat.
So you mentioned before that the wetland, the inflow to these wetlands is coming from that watershed. And that's kind of something that we think about, that point that the inflow to the wetland, that's also the outlet from that watershed above, right, which kind of serves as the point where water, sediment, nitrogen, and phosphorus are delivered to the stream. Maybe can you talk about the importance of monitoring at that scale and what that allows us to look at as we go forward into the future at some of these sites?
Yeah, so right, so we refer to that monitoring at this scale as delivery scale. So imagine you have a 1,000-acre, primarily corn and soybean row crop landscape draining to this single point. And we can measure at that point with close interval sampling and close interval flow monitoring the amount of nitrate, total nitrogen, total phosphorus, reactive phosphorus that would have been delivered to the stream had the wetland not been there, right? So it tells us how much is being exported from these typical landscapes and delivered to stream channels. And it's really different. In the case of phosphorus in particular, the phosphorus loads we get at this scale are quite different than what are measured at the ambient river monitoring stations. They tend to be substantially lower than what we measure as reported at the ambient monitoring stations.
So these systems then, as we think toward the future on some of these sites, they can kind of serve as test areas to see what might happen if we change practices in the landscape.
Right.
How might that impact what's then delivered, in this case to the wetland, but if the wetland weren't here, to the downstream stream in that case.
Right, right. In fact, there are at least a half a dozen research projects that have leveraged on top of the CREP monitoring. This site, I think we have 8 years of continuous data. Another site in the story just 10 miles to the east of us as a comparable site. We have about 7 years at that site. Some of those sites have had practices like cover crops put into place by monitoring and comparing. So monitoring at the delivery scale is being leveraged pretty heavily, both for studies having to do with the effects of practices on nitrogen and phosphorus export, also effects on the hydrology from those systems, right? The monitoring at the base of the wetland, these are really stacked practices. So if in one of these catchments, like the one 10 miles east, where about half of that catchment was put into cover crops, that's a substantial practice. We know how much the cover crops affected it because we measure at the delivery scale, and then we stacked cover crops on top of a wetland at the bottom, and we measure how much the combined effect is of the cover crops and then the wetland. Right? So researchers are finding it to be a really valuable asset.
You mentioned about the watershed kind of 10 miles east of here, and so actually as part of the learning farms and with support from the Iowa Department of Ag and Land Stewardship and the NRCS, like you said, we worked in that watershed to get about 50% of the acres implemented with cover crop. And we also have a site in Floyd County where we have with about 60% of that watershed in cover crop, and then a comparison watershed where we've had no intervention to implement cover crops. We started those with cover crops getting seeded in the fall of 2017, and so we now have a couple years of data with cover crops being seeded in the fall of 17, the fall of 18, and now the fall of 19 as well. As we look at some of that water quality data from 2018 and 2019, at least to date, we don't see a big measurable decrease in nitrate concentration or load from those watersheds where we implement cover crops. Now, one thing might be the fall of 17 and the fall of 18 and into the following springs were not good cover crop growth periods, but I think it's important as we think about that, what might be some reasons why maybe we don't see what we'd expect. Some might be it takes a long time. Some might be that you know, the cover crops did not grow as much as we'd expect. Some of it might be that maybe we aren't seeing quite the performance that we did from the plot scale research. I don't know if you have any thoughts or any comments on that.
Yeah, so the scale is a real concern, right? A lot of the early research on wetlands for nutrient removal was done in experimental wetland plots, right? And the things don't really scale up the way you'd expect them to, right? So the only way to really know is to have a full field scale system operating as intended and measure its performance. And you and I have had this discussion before. The real strength of that delivery scale is we've got 500 to 1,000 acres with enough practice implementation that we should be able to see a reduction. If we don't see a reduction at that scale, then that suggests that maybe there are other things in place, maybe we will see a reduction, but if we never see a reduction at that scale, that suggests that the small plot scale studies really aren't telling us how things behave at full scale.
And I think that really illustrates why it's so critical to monitor at that scale, but also that we do need to look at kind of a length of time, because there could be some factors. I mean, maybe or maybe not, you know, that we don't know for sure the water that's coming out now, you know, some of that was probably coming out, or that water was coming from when the cover crop was there, but there could be some lag time in this whole system that we don't see an effect. But I think it really does argue that just a 1 or 2 year monitoring period may not be enough as we think about these larger scale type systems. Yeah,
and people have frequently suggested, not only for phosphorus, for nitrogen as well, that there's a lag time at large scale, at large river scale, right? It's not clear how much of a lag time there is at 500 or 1,000 acres, but that's a possibility, right?
And that really that's why it's so critical to monitor at that scale and to continue to monitor so that we can see, you know, whether we start to see a change, and then maybe how weather factors might influence the reductions, or how the weather factors might influence the loading that we see from those systems.
Yeah, it's kind of telling if you've been around long enough, you remember the PIC year, the payment in kind year. You could see in the water quality an immediate signature of all of those corn acres being idled. There was no lag time. You saw it immediately. So it's a question we really need to get a handle on. Is there a lag here? If we're not seeing the response we expect at this scale, is it a scale problem? Trying to scale up from models or from plots, or is it a lag time problem?
And for those that maybe aren't as familiar, that maybe don't have as much gray hair as some of us, that the Payment in Kind program was a program in the 80s that would idle, in some cases on the order of 20% of the corn acres, and would have planted a small grain, a lot of times oats, in those acres in that year. And like you said, in some areas they saw an impact, a positive impact of that on the water quality.
Just in that 1 year, you immediately saw it. For nitrogen, the impact was immediate.
So in some cases, maybe we don't know, kind of, we think about and get the question, how long do we need to monitor? So we think about these delivery scales where we have cover crops. You know, question is, you know, how long do we need to monitor? You know, it seems like we might need at least 5 years of data, but even some of that might depend on the type of weather conditions that we would get. Hopefully within that 5 year period, we might see some response to the practices that we're implementing. But
yeah, Yeah, I think it's likely to be more on the order of 10 years, because if you think about what are the chances when you tend to get wet years and dry years, you tend to sometimes get a couple of them, right? So if you've only got a 5-year period, you could have had a couple of really bad growth years for those cover crops. Yeah. 10 years may not be long enough, but 10 years ought to be long enough that at least the weather effects, that ought to be enough to average it out, right? The lag time, that's really, yeah, we really don't know how long the lag time ought to be, but just in terms of having something that represents a more average condition, 10 years are probably a better target. Yeah. 5 years is certainly better than 1 or 2 years.
Yeah, 1 or 2 years, but yeah. The more the better. But we got to, hopefully at some point in time we start to see some impact so that we can.
So a colleague used to say that 3 years of data is the worst, right? 1 year's data is better than 3 years of data, because if you only have 1 year data, you don't have enough data to draw conclusions. If you have 3 years, you might think you do, and it's clearly not. You need 5, 10 years of data.
So that kind of brings up an important point. I think both you and I have been very fortunate to work on projects where we've been able to monitor for a long time, so to speak. 5 years, 5-year phases, 10 years in some cases. And so, I think that's an important point that, we both had funding specifically from the Iowa Department of Ag and Land Stewardship that have really helped us, thinking about back to these wetlands, that you've been able to monitor some of those, like you said, for this wetland on the order of 8 years. So you've had that monitoring. This is a site that actually I think it's been more than 8, because we're at 2020 right now, and this system was being monitored in the floods of 2010, if I remember correctly.
Yep, it was.
And so we think about this as a system that has had wet years, dry years, and maybe more average years. And so I think it's important to note that there are some really great examples of projects that we're fortunate in Iowa that we do have some long-term data sets on the performance of some of these practices. Yeah,
the IDALS, Iowa Department of Ag Land Stewardship, has really their support has been a game changer for some of this stuff. The Gilmore City plots, the monitoring at this scale, the Target Watershed project, all rolled in. Having that kind of long-term sustained support for this scale of monitoring, I don't think there's anywhere else in the country that has a comparable set of sites.
So I think it's also important to note, a lot of those IDALS funds have come from the ag management account with the sale of ag chemicals and fertilizers in the state. So I think it's been a really wise use of those dollars in investing in technology. I also think it's important to note that the Leopold Center for Sustainable Agriculture for a number of years was very important in kind of providing seed funding at times to get some of the research done on some of these practices. If I'm not mistaken, they helped very early on in some of the pilot scale wetlands work you might have done, and then they're also involved with some of the riparian buffer work that's been pretty important.
Yeah. Leopold and even Water Resources Center provided some small seed money for some experimental wetlands work that we did early on, and for a lot of the other practices you talked about, that's been a source of typically experimental research. Not for the kind of long-term, full-scale monitoring that we've been doing here, but 2 or 3 year long projects that let you explore a particular practice. Yeah.
And that's kind of where now with the Iowa Nutrient Research Center, we're doing some of that work as well on some new practices and getting some proof of concept or new ways to look at these practices in there as well.
Yeah. The Iowa Nutrient Research Center is really probably the go-to source for funding that kind of experimental work today.
I want to really thank you, Bill, for taking the time to come out here and visit about a host of different subjects, and certainly thank you for the long-term partnership that we've had great opportunity over almost 17 years to work together. I'll just say I think that it was about 18 years ago this summer that I came to see one of the first wetlands that was installed even before I started at Iowa State, and got to meet you. And so it's been a real pleasure to work with you over all these years, and really want to thank you for taking the time to visit with us today on some of the wetland concepts and other concepts.
I'm really glad to be out here, and thank you for taking the time to ask the questions.